Okay, so our next speaker, sorry, last one for this session is Ievgen Nedrygailov. See if I did it
Yeah,
right.
no worries about this. My name is Ievgen.
Or
My name is Ievgen. I'm
Ievgen?
from University College Cork.
Okay,
Yeah.
go ahead.
Thank you very much. So I'm in a quite good position because lots of things have been already explained before. And also this is a last talk, means that I don't have limit. So I want to use the situation and first of all, thank organizers, because it's a very good atmosphere in here, very nice presentations. And after a long time, I feel very comfortable because every second speaker starts with the wording that he or she is not an expert in thermoelectric community. And that's how I normally start my presentations. So I'm not an expert in electric chemistry, in thermoelectricity. I'm not an expert in wood. And every time when I present this to people who understand wood, they don't know anything about thermoelectricity. When I talk to people who know thermoelectricity, they don't know anything about wood. So I hope I will be able to deliver it to you, this presentation today, in a nice fashion. And so my presentation is about Nanowood, which is renewable, biodegradable, environmentally friendly material, which is hopefully will be developed soon in new material for thermoelectric generation. So, and just to start with, so I came from here. This is City Cork. It's second largest city in Ireland, located in southwest part of it. Irish people call it the true capital of Ireland, or rebel city. And the Cork city is very nice, very beautiful place. So if you have any chance visit it, I would highly recommend to do it. And this is a picture of our university. It's University College Cork, located just in the city center. And again, very quickly here, we all know that we depend on energy, and we also know that we produce lots of energy. Every year, the amount of energy we produce and consume is increasing. The dependence is close to exponential. Unfortunately, most of this energy is produced to use of fossil fuels, so we just burn them and make heat. And again, this was explained just a minute ago. There are good heat and bad heat. So the good heat is this high temperature heat, which we can use to make some useful work. We can drive turbines, engines, and produce electricity and so on. And there's lots of heat, which is characterized with very low temperature, which is called waste heat, which we're not currently using, but at the same time, like it is like 66 to 70% of total amount of energy we produce. So it's really like a huge source of actually free energy because we produce it anyway. So it comes as a side product of other industries. So we need to find a way how to use it in an effective fashion. And one of such a ways to convert heat, low-grade heat into something useful is use thermoelectric energy conversion. And again, I will not go into detail here. For solid-state devices, it's quite well known and based on this Seebeck coefficient in highly doped semiconductors. There are pros and cons of this process, which people often mention in literature. So it's a direct conversion, nothing moves, nothing emits pollution. So it's very good from one side, from other side. It's quite expensive. It's still low efficiency. Semiconductor materials themselves are quite toxic. So it's all well known. I want to mention here another point related to these materials. It's the fact that so we have right now this idea to transit to a new type of energy and economy, and we are desperately searching for raw material for that. And if you look at this map, which shows distribution of critical raw materials necessary for this energy transition, we see that most of these materials are actually in Asian countries. And nothing like that can be found in Europe. For example, bismuth, you can see that 71% of it is located in China and 14% probably it's Indonesia. So nothing like this is found in Europe. And this means that if we want to increase the amount of thermoelectric devices, we want to scale up technology, we will need more of these materials, which we don't have. So we will need to export them, which will increase the price even more. So it's not the way how to do it. So we decided to look for alternatives. And one of the alternatives is using ionic liquids or ionic electrolytes. And again, I'm not going to detail here because it was well discussed before. Very basic. So we have a bulk electrolyte in equilibrium state. We have some ions, positive and negative ions. They are in a state of equilibrium. So everything is electrically neutral. And if we create a temperature gradient across this liquid, we can see that ions will separate, and they will have a tendency to increase concentrations along the cell, so that in one place we can have predominantly positively charged ions, in other place we can have negatively charged. So we'll have special separation of these ions, which is quite well known as a Sorek effect, and which results in creation of this distribution of ions in presence of temperature gradient. And it can be used to produce some electricity, because these ions charge and we separate them in space, so they create also potential gradient. And if we look in literature for bulk electrolytes, this Seebeck coefficient, which is of course not Seebeck coefficient, but we can call it like this, is quite small and normally less than millivolt per Kelvin. So of course, this is not enough to make effective device, and we want to increase this. And so we decided to look for a way for that. And one of our partners recently found it theoretically. So what I've shown you right now is just theoretical prediction, which is not proven experimentally yet. So what they did is they just decided to study what is the effect of electric field on this Sorek effect. And the idea they had that if you have this electrolyte and place it inside of a nanochannel, and we know that when we have a contact between liquid and solid, on the surface we create an electric double field, which results in formation of a surface charge. And so if we have a nanochannel which have a characteristic size comparable to width of this electric double layer, then the whole volume inside of a nanochannel is charged. And so if we place our ions in this electric field, we can see significant deviation from the bulk behavior. For example, here on this picture, you can see this is non-dimensional Seebeck coefficient. So Seebeck coefficient divided by the surface charge, which is for this calculation was 1575 and 125 millivolts. And the x-axis is actually the ratio between the characteristic size of a nanochannel, like width of this nanochannel, and the width of electric double layer. And as you can see, for example, if we look at this one means that the width of the nanochannel is comparable to electric double layer width. And as you can see, if we go to this direction, where we definitely have a nanochannel fully inside of this electric double field created by electric double layer, we can see that we have quite significant Seebeck coefficient, which is actually 1, so it's equal to the surface charge density. And if we go to wider channel, it's quickly decaying, and so this means that this effect disappears if we go to bulk-like behavior in the electrolyte. And actually, 0 here means not like 0 of Seebeck coefficient; it just we come to a normal Seebeck coefficient characteristic for this liquid in bulk state. There was a similar calculation recently published by another group confirming the same. So they use different model, different type of calculation, but they came to the same conclusion that if you place an ionic electrolyte in a nanochannel and start decreasing the width of this nanochannel, then at a certain number of width, so which is for this cases like less than 2 nanometers, you have a significant enhancement of the Seebeck coefficient, which is from something close to 0 goes to something like 30 millivolt per Kelvin. And from here, from this pure theoretical prediction, we can conclude that if we place our ionic electrolyte in highly charged nanochannel, we can expect significant enhancement of thermoelectric effect. According to these predictions, it's up to 30 times, but of course, it's not necessary that we have exactly the same number experimentally. So we wanted to test this experimentally, and for that we needed to find these nanochannels. And this is a difficult thing because we have nanofabrication and we can fabricate a nanochannel. But one nanochannel will not be able to produce much. So to be able to have a decent amount of electricity produced, we have to have like a membrane composed of like many nanochannels. So we basically need to have something containing like thousands or millions of channels. And it's very difficult to fabricate it artificially. So we decided to look for some other materials. And that's our pathway to wood. So first we can calculate the Debye length, which is basically characterizes the width of electric double layer. And as you can see, if we calculate it as a function of concentration of electrolyte, we see that there's a clear tendency that for higher concentration of electrolytes, the width of electric double layer is much smaller. And if we talk about like normal capacitors, thermoelectric cells based on ions, we normally work with quite high concentrations on the order of moles. So I call it ordinary solutions. And we can see that for this kind of systems, the Debye length is close to zero, which means that in such conditions, there is no way to observe this enhancement of thermoelectric effect due to nano-confinement effect. And what is realistic to fabricate is something like 30, 20, 10 nanometers. So that's what we can do in lab. That's what we can find in nature. And for having such nanochannels and observing nano-confinement effect in them, we need to go to lower concentrations of electrolyte, something like 10 to -3 or less than that. And so we were searching for a material which can give us like lots of these nanochannels and which can be in the range of like this 10 to 30 nanometers. And then we found wood, because we know that wood is a quite complicated material where we can have these fibers of cellulose. They are long, very well aligned, and they are of the size which is very promising for us. And if you look at this SEM image at the same time, you see that there are no channels because something is covering these cellulose fibers, and there's lots of other material. And I'm sorry for my very bad drawing skills, but that's what I was trying to explain here. So we have the cellulose fibers, which are shown here as these yellow lines. And in a normal natural piece of wood, this space between these fibers is always filled with what is called lignin and what is called hemicellulose. So lignin is natural polymer. Hemicellulose is also some sort of fibers. Altogether, it makes the structure very mechanically stable. And at the same time, altogether, it makes it not membrane interesting for us. There are some big scale, micro scale channels to transform liquid for the wood, but that's not what we're looking for. So that's why we need to make some chemical treatment, which is called delignification. And this treatment results in removing of lignin and hemicellulose, leaving just cellulose fibers. And we have lots of space between these fibers where we can put our ions, and then these ions will be like in a channel, in the nanochannel. And then we can also bring some charge to the surface of these cellulose fibers, and then we will have charged nanochannels. And this is very similar to what people were doing for like thousands of years by producing paper, except for we are trying to make the procedure very carefully so that we do not destroy the structure of natural wood. So just a few pictures. That's, for example, a log of natural wood. And this is a piece of cellulose we produced after treatment. As you can see, if we do it carefully, we can preserve even the shape of the log. So it does not break and fall apart like it happens when we produce paper, for example. And this picture shows, unfortunately, it's not very well seen, but you can see these are actually our membranes, which we can produce in the same way. So we can cut wood in a certain shapes like square, rectangular, anything. And then we can carefully delignify them and produce this white and nice looking cellulose membranes. And then we can assemble an ionic thermoelectric cell in this way. So this is a plastic case. Inside of this case, somewhere here, we have a cellulose membrane, and then on top and on the bottom we have metal contacts. So we use different electrode materials depending on what kind of electrolyte we have. For this picture, I guess it was stainless steel. Before closing the cell, we infiltrate it with electrolyte, and when we close it, it's sealed, so it prevents evaporation of electrolyte. And first, before I switch to thermoelectric properties, a few words about characterization of these membranes. So we need to make sure that we have nanoconfinement, and for that we use just electrochemistry, electrochemical impedance spectroscopy, because we can measure resistance of these membranes. And if we do it, we receive such a curve. So here we have a resistance of our electrolyte in a membrane, measured between two platinum electrodes placed very close to membrane. And as you can see, this is a resistance as a function of concentration in log-log scale. And if we first look at sodium chloride electrolyte, bulk electrolyte, so there is no membrane in here, we see that it's linear relation and what it should be. And if we make the same experiment with Nanowood, we can say that first at very high concentrations, we see quite similar behavior, and that at a certain point, somewhere here, we see that the curve goes in a different way. And that's how we explain it. So if we take this very general equation for conductivity of electrolyte inside of a nanochannel, we can see that it looks like this. So we have two terms here. One is representing bulk conductance. So we have here mobility of ions, concentration of electrolyte, and geometric parameters of our cell, like width, height, and distance between electrodes. And this term is representing conductivity due to a surface charge effect. Here we have surface charge density, width, and distance, or in this case, it's length of electrolyte, nanochannel. And of course, if we go to very high concentrations of electrolytes, this will dominate. And the whole conductance, or in this case resistance, which is opposite to conductance, will be just a function of concentration, because this will be significantly bigger than this one. But if we go to very low concentrations, this first term becomes very small and everything starts to dominate by the second term, surface conductance. And since it is not related to concentration of electrolyte, then this resistance goes to plateau. And this is a clear evidence that we come to this region where we have nano-confinement effect. So we can clearly see that we have two regions here, bulk conductance and nano-confinement. So, and this means that if we want to observe this thermoelectric enhancement, we should look at these concentrations of electrolyte, like less than 10 to minus 3. So first attempt to confirm that we have enhancement of thermoelectric effect was made using measurements of current voltage curves, and it is shown here. And as you can see, so first, this is a current voltage curve and of a cell with a membrane infiltrated with sodium chloride electrolyte. And if we measure IV curve at thermal equilibrium, so delta T is different, 0, we have a nice linear curve, which comes for the zero point. When we start applying some temperature difference, we see that there is some change. So first of all the curves become non-linear. And this is quite easy to explain, because when we have one side of the membrane at higher temperature than another, then electric double layer width also changes, and the nanochannel becomes asymmetrically charged. So the whole curve becomes more like diode-like curve because of that. And we can also see that the whole curve is shifting. So we do not cross this at 0, 0 anymore. So there is some potential in here. which is changing when we increase the voltage. And there's also some current, but later we just realized that this current is not really good to measure in this way because it is time dependent, and it depends on how quickly or how slowly you make this measurement. Yeah, but anyway, we were able to see this effect. Later, we switched to something more similar to capacitor characterization when we have this on and off of temperature gradient, and then we have this charging and discharging curves. And here you can clearly see that this is exactly the same experiment, everything the same except for electrolyte concentration. So this is 1 amp solution, and this is 0.1 milliamp solution. And here you can see that for the same temperature difference, for the same everything, we have quite significant enhancement in terms of thermoelectric voltage. So a short summary. So I hope I was able to convince you that the lignified wood can be seen as a new material for making thermoelectric devices. And also I showed you some very first results showing that electrolytes confined in space of charged nanochannels can show significantly higher thermoelectric performance. So if you are interested in more details, I would highly recommend you to visit our website. So we have 2 projects. One is called Translate project. It is funded by European Union. Another is NextGen Wood, funded by Irish government. This is our team. And thank you.
Thank you. Any questions? Yungao from Japan.
Thank you for your talk. Do you have SEM or TEM image to show your nanochannels? What's the diameter of the channel?
Well, it's no, I don't have it here. It's a huge challenge okay. because this material is very soft. So you cannot polish the surface. And so there are some procedures used in biology when they have like special devices to slice materials like this while they are probably freezing in like liquid nitrogen. We didn't do it yet. We're working on this, but no, I don't have it, and it's very difficult to make it.
I see.
More questions? Oriano from Bremen.
Thank you. The question is similar because I'm very curious to understand what is really the structure. Because when I think of wood, I imagine the inside of a plant where there are the cells and the channels where the liquids flow. So what is the picture you have in mind? Those channels are aligned along the length of the plant?
Yes, it's quite complicated structure when you take a natural wood. There are lots of micro channels, there are lots of vessels. Some of these channels, so for materials like I don't know, bamboo, or if you take some tropical materials designed for transporting large amount of waters, these channels can be even like on the millimeter scale, so you can see them with the naked eye. But when you make the lignification, you basically collapse all those structures. Nice. And then if you do it in a proper way, when you from one side chemically remove lignin and hemicellulose, from other side mechanically kind of trying to apply a little bit of pressure so that you hold all these fibers together, you can collapse all these internal structures, and then you get something like like similar to closed pack structure, when you have just lots of these fibers very well aligned and just placed one to next to another. And then since they are round, so you just have these channels in the space between them, but you don't really have micro channels or something big. And we can easily control it using electrochemical impedance spectroscopy. So you can definitely define the case where you have these large channels and then the whole structure behaves like bulk electrolyte. And then, for example, if you go back to this picture, you will always get this, just typical behavior for bulk electrolyte. Maybe the resistance will be higher or lower, but the same trend. And then if you do membrane in a proper way and you have nano-sized channels and you don't have any kind of bypass channels through microchannels, then you start seeing this nano-confinement effect. So we can't see it with our eyes, but we can control it by measuring conductance as a function of concentration, for example, using EIS.
My curiosity, if you cut the material in the wrong direction instead, you see that it is insulating. Did you ever try?
Yeah, so I don't have this probably here. So basically, these are our fibers, and we make it so that this is hot side, for example, and this is cold side. So the channels are coming from cold to hot side. We don't do it other way around. Probably you will see something as well, but I didn't try it, so I can't tell you what happens if we change the directions of
You
it.
expect that it is more insulating and it does not work anyway.
Well, since we don't have a clear mechanism how exactly ions moving inside of a nanochannel, so this kind of behavior can be not as what we expect for bulk liquid. It's difficult. So it's some sort of hopping on the surface of highly charged channels. So that's why it's difficult to say. But I would expect it will be significantly lower, but it's difficult to say because we didn't do it.
Any other question?
Yeah, I have a little question is that does the materials will be easily be broken? Because you see the picture when you have after treatment, it will be easily broken when you use it.
So the material is soft. And if you take it in your hand, you can easily break it. So you need to work carefully with it, or you need to freeze it when you move it some. Yeah, so it's easy to break the material.
Yeah, change away from ISD in Japan. So can you show me your current voltage scan again? So I don't work in the system, but I feel that if you scan from larger than the open circuit voltage and the short circuit current range, okay, actually you are charging your device.
Mm-hmm.
So that could make the curve change. I guess, I don't know, because there's no electron transfer between your ions and the electrode. So I feel that for this system, probably it's better to determine the open circuit voltage first and scan from the open voltage circuit to the short circuit current, but don't overlap the range. That is what I feel.
Yes, totally support this concept. And just like I mentioned to you before, that the current showing on these IV curves is time dependent.
Okay.
And then, so this made using electrochemical potential stat, where you can control the scan rate. And if you start changing, you see that the current is changing. So I mean that that's why we switched to more like this open circuit voltage as a time dependent, because it gives a more reliable data. The current is always there because the circuit is closed, but it's very difficult to measure it and convert to something like similar to what we use for batteries, for example. It's not that defined. Yeah.
Okay.
I agree with you.
Thank you.
Have you tried measuring at a steady state current voltage?
So there's no really steady state here in terms of current. So so there's certain time you need to make this IV current measurement, and then you repeat it and you see that the potential is more or less there, but the current is going to lower and lower values. So it's more like behaving more like a capacitor, which is charging and which is connected to some non-ideal circuit where you have some, some discharge and charging at the same time.
Okay, thanks. Any other question? No, so thanks, Eugene. So that's the end of the session today. So now we have the coffee break and the posters, and then we'll go to the gala dinner. Remember, those who want to come here to go to the restaurant, please be at the reception at 8. Okay, we'll try to leave on time, to stay there around 8:30. Okay? If you miss us, just go along the promenade and you will find us.